Today we are talking about AI powered image generation, which we have understood. We have seen some tools regarding AI powered image generation on the previous lecture. Let's go back what we have understood. We'll have a quick recap of that. These are all our agenda. So we have understood about what is text input. We have understood about how we do the text encoding into the numerical representation, how we do the text to numerical representation by using text encoding format. Then we have understood about image generation, how we use it, how we learned our data to do convert the image and generate an image from an encoded text format. Then we have understood about the first tool of it, like which is stable diffusion. Okay. Then we have understood about the architecture of the stable diffusion, how it works, and the applications regarding stable diffusions. These are some of the advantages and limitations with respect to stable diffusion tool. Then we have understood about the mid journey. Okay, so this is all. This was also a high level photo to image, like what we can say photo. Call it what we are doing here. We are converting our text format into the encoded format, and then we are generating our images. Okay. Then these are all the, by giving some prompt engineering techniques and using the LLM, we are supposed to do this. These are the working procedures of it. We are using encoder decoder architectures, and from that we are using a GAN architecture, which is a generator and discriminator. Okay. These are all the advantages and disadvantages with respect to mid-journey tool. Then we have seen CLIP, which is a constructive language image pre-training. Okay, so here we were looking at the working of it. We were looking at the architecture. We have gone through the architecture of it, which was following a vision transformer architecture from a which is a self-attention mechanism architecture, which is following a self-attention mechanism architecture. Then we have seen some of the applications regarding CLIP. So let's have some architectures and applications with respect to CLIP. So firstly, we'll understand about what is CLIP. So CLIP is a multimodal learning architecture which is deployed by OpenAI. CLIP is a neural network which is trained on varieties of image text pairs. CLIP, that is constructive learning image training, is a cutting edge AI model which is developed by OpenAI. Okay. And at the end, what we can say, it is applicable in various domains such as computer vision, natural language processing, and many more. Here we are using zero-shot learning capabilities for giving the prompts. CLIP. So how it works? CLIP works on two main components. First is a encoder, a text encoder. We are going to convert a text into the encoded format, and then we are using the image encoder also. Here we are using our image and we are forming that image into the numerical format, like pixel, smaller size pixel format. Okay, which will be a numerical representation of an image. The text encoder process will have a textual inputs into the embeddings, and the image encoders will convert the image into the usual embeddings format. Okay, the images will convert its usual embedding format, and text will convert it, whatever the text format it is having, it will convert into the numerical embedding format. Both the encoders are then trained to the projects, and then the text and the images into the shared embedding space. It will be there in this shared embedding space. It uses a large scale data sets of an image as well as text pair for training. Okay, we have to have large range, large scale of the data sets of text also and images also. Then it employs a constructive learning to match corresponding text image pairs among the batch of negative pairs. The model is optimized to minimize the distance between the correct text image pairs. It will maximize the distance between the two non-matching pairs, and it will increase the vice versa will occur. It will maximize the distance between non-matching pair and minimize the distance between the matching pairs so that we can have understanding about both the pairs. It leverages a large corpus of text and images without manual labeling it. Okay. Then it utilizes transformer architectures for both text also as well as image encoding as well. Okay. So it is using a transform architecture. So here in the text encoder, transformer based model is optimized for textual inputs. And for the image encoder, we are using vision transformer. Or we can say the RESTnet based models for image inputs. And then what we are doing? We are making the encoder numerical representation of that image as well as of the text. The shared embedding space allows for the comparison of textual as well as visual data. Okay, so after that, we are taking both the encoders from the text as well as image, and we are training both simultaneously to learn the alignment between the two. Then the model is trained on diverse sets of data sets to ensure the robustness and generalizability. Then there is zero-shot learning capabilities. Yes, it has a zero-shot learning capability stems from this will generate a embedding space between each other. Okay, then this architecture will support various image resolutions. Like we can use it for like zero-shot predictions, like giving the input and we'll get the output suddenly, just giving one shot embedding, or what we can say one-shot predictions we can get. See what is here. So we can get a direct answer like one-shot prediction we can get from here. Apart from that, it is scalable for different sizes, different data set sizes and complexities. It can be fine-tuned options is available for specific applications. Like if you want to do it for specific other purpose, we can fine-tune this model for the other purposes and it can be applicable. It emphasizes the importance of a balanced data set to avoid the biases. Okay, so we should have a balanced data set before going forward. Then the applications of it are, it has a zero-shot learning. It enables the image recognitions in categories. It wasn't explicitly trained on. Okay, using a textual descriptions. Then there is image search. Image search will allow searching for images using natural language description. It improves the accuracy over keyword-based searches. Content moderations. It helps in identifying and filtering inappropriate contents in the images by understanding their context through text. Then there is augmented reality interaction. It enhances what is augmented reality, which is AI, AR. It enhances the experience by letting users interact with virtual environments through a natural language commands. Then there is mutual question answering. Answers questions about images, understanding both visual content as well as query text. Then to provide the accurate responses between the two. Like we can use both the visual content as well as we can use the query text format also for making the correct or accurate response. Then these are all the advantages and disadvantages with respect to CLIP tools. So firstly, it is a multimodal learning. So advantage of it is it understands the relationship between the text as well as images. Okay. And the disadvantages with related to multimodal learning is it requires large amount of data to train. Yes, it will require large amount of data, both the textual as well as images, both the data will be required. Zero-shot learning can be applied to new categories without adding training data. And what we can say about disadvantages, if the unseen categories come, for example, it will give a very less accuracy or as compared to that of fine tuning the models. Okay, if we explicitly want to fine tune the model, then it will give good accuracy. But for the same model, if we want unseen data to be there, it will give less accuracy. Then there is transfer learning. Transfer learning can be fine tuned for specific tasks. It depends on its improving performances. Then disadvantages with related to this is it requires specialized knowledge and resources to fine tune that. Okay. Then there is versatility. It is applicable to various tasks like image retrieval, image captioning, and virtual question answering. Okay, for all these purpose, it is good. Like for different purpose, we can use it according to our purpose. But what is the disadvantages then? The performance can vary depending on the specific task and the data set. Okay, how much we have trained on that part, that depends on the performance. Okay, then interpretability. It provides insight into the model's reasoning through attention mechanism. Okay, so whatever we are doing, we are providing some insights upon the model's reasoning through attention mechanism. Like whatever will be the past knowledge it is having, like that, all the thing will be depending on this model. Since we are using the transformer architecture or transformer model, so it will depend on that. But the disadvantages with related to this is it requires expertise to understand and interpret the results. Then there is again different model, which is BLIP 2, which is a bootstrapping language image pre-training. A model for bootstrapping vision language, which is a pre-training efficiency model, which aims to address the high cost of training large-scale visions and language models. Okay, so it has high cost for training is required, like for vision as well as for language models both. Okay, it leverages the pre-trained images, encoders, and large-scale models like LLMs as a building blocks. Okay, then it introduces a lightweight Turing transformer to bridge the gap between visual as well as language modalities. This Turing transformer is pre-trained on two stages. First is our representation learning and second is our generative learning. So this achieves the state-of-art performance on various usual language tasks despite fewer trainable parameters. It can be used for conditional text generation based on the image and the optional text prompt as well. Primarily, it can be used for research purposes and not yet widely adopted for commercial applications. Okay, so this is not commercially, we can't use it for like commercial applications, but we can use it for research purposes and other stuffs. Okay, then BLIP 2. BLIP 2 starts with pre-trained image encoders and language models that are kept frozen to save computational cost and prevents the catastrophic forgetting. A lightweight Turing transformer, which is Q-former, bridges the modality gap between vision and the language. Okay. So this Q-former is a pre-trained model which is forming a two stages for efficient learning. First stage is for it bootstrap vision language representation learning from the image encoders, just what we have seen in clip. Okay, it is also multimodal only. Okay, so here we are using first for vision language representation learning from image encoders, and the second step or the second stage is vision to language generative learning from the language models. The Q-former employs learnable query vectors to interact with image features and text which will optimize the vision language alignment between the two. Multiple pre-training objectives such as text image contrastive learning, image grounded text generations, and image text matchings are used to train the Q former, which is one of the two. Okay, for generative pre-training, the output from the Q former is projected to match the LM's input dimensions, which will serve as a soft visual prompts. Okay. Then there is blip 2's working, how it works actually. So this method will allow zero-shot image to text generation capabilities from the natural language instructions. So this blip 2 will achieve a state-of-art performance on several vision language tasks with significantly fewer trainable parameters than existing methods. It demonstrates emerging capabilities in zero-shot image to text generation. It will have a visual reasoning and a conversational, what we can say, a conversational chatbot types. The architecture is designed to be modular, allowing for updates and improvements. Yes, this architecture is designed for modular, allowing updates. Continuously, we can update it and improvements as the new model becomes available. So whenever the new model will come, it will update it. Okay, so this architecture is built on the modular approach. So that is one of the good. Then, despite its efficiency and lower parameter count, Blip 2 will outperform large models like Flamingo 80 billion on specific benchmarks. It suggests a future directions for building more compute efficient and effective vision language models. Then this Blip 2 will open possibilities for advanced applications in multimodal AI. Then it will combine the strength of vision as well as language understanding and blend the two, vision as well as language. Then it has learnable query embeddings. The Q former uses a set of learnable query embeddings as an input. Okay. Then which will interact with the image features through cross attention layers and textual information through self attention layers. Okay. So what is this layers are? Hidden layers. So these queries extract and refine visual features that are most relevant to the text. Okay, it will extract the what it will do. Firstly, it will take query embeddings as an input from the images as well as from the text information, and then it will extract and refine the visual features that is relevant to the text and match them both. Then the transformer submodels. The Q format comprises two transformer submodels that shares the self-attention layers. An image transformer for interacting with image features and a text transformer that functions as both a text encoder as well as decoder. Then there is self-attention layers. This self-attention layers, what it will do, these layers are learnable queries to interact with each others. And with the text token, enabling the dynamic feature extractions and representation learning, all these will be learned. Okay, whenever the new query will arise, it will learn from the all like text to embedding to dynamic features, what is there in our representation learning. It will go inside our hidden layer and it will work further and then give us the final output. So these are all the advantages as well as disadvantages of Blip 2. So first advantage is efficiency. Lower training cost as compared to that of large-scale vision language models. As we have seen, Clip will having a large cost because it will have huge numbers of data set we will require. So here there is lower training cost because we are not taking that much data compared to that of large scale vision language models. Then disadvantages is may not be as effective to very specific task or very specialized task, what we can say. Then the state of art performance, as we have seen, it achieves the high accuracy on various vision language benchmarks. And the disadvantages with related to this is performance might degrade with the limited or noisy data. If like biased data will come, unbalanced data will come, so it might degrade its performance. Then there is modular design. It leverages a pre-trained components which will allow for flexibility and customization. The disadvantage with relative to modular design will be it requires expertise to fine tune and adapt to specific application. Then there is conditional text generation. It can generate text description based on images and prompts. Okay, but what is the disadvantage then? It may struggle with complex or nuisance language concepts. Okay, then there is accessibility. Code and pre-trained models might be available for research purposes. But the disadvantage with related to accessibility is it will primarily research orientedly used. We can use it primarily for research purposes. Not yet it is widely used for commercial purposes. So that is one of the main thing. So these are all the applications with respect to blip. It has first image and text matching. Yes, we can blend the image to text matching between the two. So blip 2 excels at matching the images and text description. This can be used for image retrieval task, where users can search for images using natural language descriptions. Okay. Then there is image captioning. It can generate detailed and accurate description for images, aiding tasks like image understanding for visually impaired users. Okay, like if you want to use it for visually impaired users, it is useful for them also because it gives like clear or what we can say detailed information or detailed captions of the images is required, or it gives or generates. Okay, or what we can it enriches the social media content also. Okay, then we can use it for visual question answering. Blip 2 can answer questions about images based on their content. This has applications in both education sectors, image analysis, creating interactive visual experiences, and so on and so forth. Improved AI assistance. By understanding both images and text, Blip 2 can enhance AI assistance. It will enable them to better understand the user queries that will involve both visuals content, visual informations, as well as the textual informations. So this was all about our Blip2 model. Now we'll understand about the vision transformer. So vision transformer is a deep learning model for image recognitions that leverages the power of transformers, typically used for natural language understanding. It breaks down an image into the patches. Okay, what we can say pixels. Okay, some small patches or some small we can say minute pixels. We can break down the image into that and we can encode them with a pre-trained CNN model. Okay, and uses this transformer to understand the relationship between these patches. It offers potential advantages over traditional CNNs, allowing the model to capture long-range dependencies and analyze how different parts of image connects with each other. Okay. So this is all about our like transformer encoders. See, we can see the the architectures with related to transformer encoders. It will first embed from the image, it will embed some patches and it will make into the numerical format. Then we will do the normalizations. Then we'll apply the multi-head attention mechanism. After that, we will normalize that. We will use our multi-layer perceptron and then we can use it likewise. It can be used for image classification, object detections, and other computer vision tasks as well. It will achieve a state-of-art performance in some cases. This vision transformer working in architecture. So firstly, what we are doing, we are taking our image embeddings. The input image is divided into a fixed size of squares. Okay, whatever is the images, we are dividing that image into fixed size of squares. Okay, which is called as patches. Each patch is flattened into the vector representations. Okay, whatever the patch we have taken, we are then making that patch into some vector representation, or what we can say in a numerical format. We want that. Okay, after that, the image also includes a class embedding. Whatever is the class. Okay, which class is this? So we want that class also to be learned according to that. What is there in this patch, in this patch, in this patch, likewise. Okay, like class can be like bird, ball, cat, and so on and so forth. It can be anything, any item which we want to analyze or detect, which represents the entire image. If in this case, we can say a building is in class here. Okay, so which represents the entire image and is prepended to the sequence of embedded image patches. Then we are doing what? Then we are doing a positional encoding. The patch embeddings are augmented with a positional encoding. Like we are augmenting, we are increasing the size of our data set with our patch embeddings. Okay, by using a positional encoding. Okay, these encodings will add information about the relative locations of each patches in the original image as well. Even though the patches are processed sequentially, like we are giving this sequentially we are giving. Okay, apart from that, we are augmenting this also with respect to positional embedding, so that our model should understand what we are doing. So this will help the model understand the spatial relationship between different parts of the image. What is the first part, second part, third part, fourth part, likewise. And augmenting with respect to that only, positional embedding accordingly. After that, we are making a transformer encoder. The core building blocks of vision transformer architecture is, it will consist of multiple encoder layers, which will stack on the top of each other. Each encoder layer will consist of two sublayers. First is a multi-head self-attention mechanism. What it will do, we will understand. And then there is a feed-forward network. Okay, so these two are present. First is a multi-head self-attention mechanism. So what it will do, it will analyze a relationship between each patch and all other patches in the sequence. Whatever we will do in a sequence format. Okay, and it will understand the sequence between these two. The first was this, second was this, third was this, likewise. This will allow the model to understand how different parts of the images relate to each other. Okay, that's how it works. And this multi-head attention mechanism, the purpose of this is only to analyze the relationship between each patches. Okay, then there is a feed-forward network. Feed-forward network is a sublayer that introduced non-linearity into the model. It will allow the model to learn more complex relationships. If there are like we are doing augmentation also, so it will analyze whatever the complex relationship will also enter. It will allow to learn that relationship and within the image data itself only. Okay, so this is our multi-head attention and our feed-forward network. Then comes our multi-layer perceptron. Multi-layer perceptron is a final layer added to the top of the transformer encoder stack. Its function depends on specific task. For example, if you want to do a classification, so it will predict the class label. Like it will predict from the given image, it will predict, okay, this image is, it will give the class label. Like it is a dog, it is a cat, it is a building, it is an airplane, likewise. And if it is a regression, then it will do a continuous value. It will give us an output, a continuous value, which will be a numerical value, such as image quality score it will give. Likewise, it will provide us. Okay. So this is it. We will see the applications of vision transformer in the next lecture. Okay. Then we'll see about DALI 3 and other parts. So these are all very interesting. And if you want a career in this field, this is like very important transformer architecture and other things. So this is it for today, guys. So let's meet on next Saturday. This is it from my side. Goodbye. Thank you for joining.